Okay, everybody, let's get started with this review problem here. If you take a look at this quadratic equation, just write it down in a place where you have some space to work and copy down the quadratic formula in blue on the right there as well. And let's just work through the process for it. So one thing we want to do when we're solving quadratic equations with the quadratic formula is figure out the discriminant. So you would do the b squared minus 4ac calculation first. Decide how many solutions there are, and if you think there will be positive solutions, you continue to solve. So going through those steps would have us solve b squared minus 4ac, and then we end up with a negative 39. So when I go to put that into the quadratic formula, I get no solution. All right, this is what we have done all the time up until now, basically. So we now have a way to deal with a negative square root, but up until now that has not been available to us. Okay, so the next thing I'd like you to do, just recalling how we deal with powers of I. So if you have I to this gigantic power, can you simplify it down and write down what that would equal? Alright, so again we want to divide the power by 4 and see where in the cycle we fall. So dividing the power by 4 is going to give us a remainder of 1. So this would just be equivalent to I, right? Because it would be I to the first if we have a remainder 1. So that's the same as just plain I. Alright, so a little bit more review in that way. I'm going to take a minute to pause the video here and work through these 6 problems. Again, any space you have, but pause here and work through them. Alright, so hopefully what you were doing was dividing the powers by 4 and seeing where in the cycle you fell. So these represent remainders when we divide the power by 4. Remainder 0 would be equivalent to 1. Remainder 1 would be equivalent to I. And remainder 1 again equivalent to I. It doesn't matter how large those powers are, we do the same thing every time. Alright, so this part here, what we should have done was use the distributive property of multiply through by FOIL, so we end up with 32 plus 8i minus 24i minus 6i squared. If we have an I squared, we replace it with negative 1, and at that point we have a plus 6 on the end, so that will combine with the 32. It should be written first, so if we have a non-complex part, that should go first. 38 minus 16i is our result. This one, when we multiply through, we get 36 and we get negative 25i squared, but everything else just cancels out. We have a minus 30 and a plus 30. So write it like this, change it to a negative 1, would be plus 25 then, so that comes out to a total of 61. And when we're squaring, we need to write the binomial twice. So hopefully that's what happened on your paper. And when you multiply through, I squared becomes negative 1, so we have negative 4 on the end, combined with a 9 gives us 5. So we have 5 plus 12i in that spot. Okay, so that takes us through all of the different things that we have done to this point with i's. Alright, so this is your homework assignment from the last section. So what we were supposed to do is try to find a path of complex numbers. So you can have a look at this. I'm just going to leave the first half up here. You can pause to see how you did with it. And here's the bottom half. Okay, so we can discuss any issues that might have arisen from that the next time we're together. So this page, I found some information about where imaginary numbers come into play outside of the classroom. So if you want more information about imaginary numbers, you can pause here and read this, and it will be also posted in the class notes, so you can find it there too. But there are applications of it, just not in everyday life. That's really meant for certain fields, but there certainly are some of you that will end up in fields like that. So this is an overview of how imaginary numbers are used. Okay, so our goal for today, we need to get through pages 22 to 24 with instruction. Your homework assignment's page 25. So let's go to page 22. So up to this point, we have solved quadratic equations 3 different ways. We have done factoring and zero product property. we have done quadratic formula using discriminant first, and we've done completing the square. If we have a quadratic with complex roots are not going to be factorable though, so we're not going to be able to apply number 1 when we have complex roots. We will be able to apply the other two. So to remind you, discriminant, as we saw in the bell work, is b squared minus 4ac. It's the part under the radical. If that part is greater than or equal to 0, we'll get real number answers. If it's less than 0, we'll get complex solutions. So we won't be writing no solution anymore in that scenario. We will get complex answers with i's and be able to proceed. So which of the following have real roots and which have complex roots without completely solving them? So you can either graph these or you can calculate the discriminant to do each one. But do pause here and take a minute to try each of these 4. All right, this first one, if you graph it, it's shifted down 6 units, so we can make a parabola that's 6 units lower than usual. And then you see 2 x-intercepts. This one we have shift up 6, so when we do that we have no x-intercepts, so the roots that are associated with this equation must be complex because we can't see them on the x-axis. For C, if you do the discriminant here, it comes out to be negative 36. So when I put that under a square root, I would need to use complex numbers, so both roots here are complex. And if I do the discriminant for D, I get a positive number. Even though it's not a perfect square, that doesn't matter. We will get positive answers, so we'll have 2 real roots for letter D. Okay, so solving the quadratic equations below using certain methods. So let's try to use the path of least resistance for each of these. So for number 1, I'm going to illustrate how we can use completing the square, and then we'll go through some other methods as well. So the first thing I want to do with completing the square is think about the middle term. I have a negative 4. When I do completing the square, I think of half of that term. So I'll have an x minus 2 quantity squared. The reason there's a plus 1 there is because I'm doing the need versus have comparison. When I get this binomial written, I'm squaring 2, and that means that I need 4 to have a complete square. But I have 5 available, which means this equation actually has a surplus of units. So it's surplus by 1. To solve that equation now, I would try to isolate this square term. So subtract 1 to the right, and we have a situation where we're doing square root negative 1. All right, we can use that though because we know that the square root of negative 1 is I. So this becomes plus and minus I. Well, it will. Plus and minus root negative 1. The root goes away on the left side, squaring a square root, or square rooting a square. And if I add 2, that goes in front. I have my plus minus, and I have my I. Okay, so that is what's considered a complex solution to a quadratic equation. I would get that same result no matter what method I use, but that works out well with completing the square. Pretty easy to do. This one, in number 2, is already set up for me to do this blue step from the previous one. So if I just square root both sides, remember the plus minus, that's always going to be there. Negative 4 square root would be 2i. So I have minus 3 from subtracting 3 plus and minus 2i. Those are probably the easiest kind when you have already a square term isolated like that. All right, number 3, my suggestion here is quadratic formula because when I cut the 3 in half, I would get a decimal. So just to avoid that, move the 3 over to the right. So I have a 0. Figure out the discriminant. So if you want to take a minute to do that, go ahead and pause. My discriminant is going to be 9 minus 4 times 1 times 3, so that comes out to negative 3. Go back into the quadratic formula and insert negative 3 under the square root sign. Remember, it starts with negative b, so that's why the 3 turned into a minus 3, all over 2a. So then, to finish this, I would take the negative out and make it I root 3. And then at the end, you can convert it to a complex number format by dividing negative 3 by 2 and I by 2. So we have that as a final result. So again, quadratic formula means get a 0 on one side, discriminant, insert, and go. All right, the last one here, number 4, we are rewriting. So I want to basically make this equation easier to use, right? I have an x squared over 2 here. I don't want that. I want to instead make it just a plain x squared. So if I double both sides, doubling the left side will clear the fraction, doubling the right side will distribute. So that's where I am. It's going to equal 0 if I move the 10 and the minus 34 to the left. So that's what I have at this point. All right, so from here, I could easily complete the square by taking half of 10. I might write it as x minus 5. This is a need 25 and have 34 scenario. So that's where the plus 9 comes from. Move the 9 to the right, square root, and solve it out. So the negative 9 is 3i, and the 5 gets added over. So 5 plus 3i. Or I could do quadratic formula. So the discriminant would be b squared minus 4ac, comes out to negative 36. Put it into the quadratic formula under the square root, and now reduce by 2. Well, the negative 36 becomes 6i first, and then I'll reduce by 2. And I get the same answer, 5 plus and minus 3i. So you choose your method. Path of least resistance, look at the equation carefully, decide which method makes most sense for you. All right, next page. Page 23. I'm going to leave numbers 5 and 6 for you to try. And again, do them the same way. In the end, these should be in this format with the regular number or fraction first, and then the imaginary part second. So 5 and 6 will work just like 1 through 4. Pick your best method. All right, in the middle of the page, the numbers 1 to 4 below, calculate the sum and the product. So that means we need to first add them and then multiply them. Okay, so we have, in the first case, 2 plus I plus 2 minus I. If we're adding, the parentheses aren't really important, but I would see 2 plus 2 is 4, I plus negative I is nothing, so I get 4. Second one, I'm going to have the same thing happen. I've got a bunch of canceling, because I've got some canceling here. I've got 3 plus 3, but the 5 i's cancel each other out. Same thing happens in 3. Same thing happens in 4. When I multiply them, every time I multiply them, I'm going to have first times first and last times last, but the middles are going to drop themselves out. So negative 2i and positive 2i, they drop out. And what I get is 4 minus I squared. Since I squared is negative 1, 4 minus negative 1 would be 5. So the product of two conjugates is going to equal a regular number, because the I term drops out and all I have is a regular number and an I squared. Happens again here. 3 times 3 is 9. 5 times 5 is 25, so minus 25i squared. Replace the I squared and you end up with just a regular number. It happens in the third one. In this fourth one, when I do 1 times 1, I get 1, but then the other part, it's I times I, so that's I squared. Root times root would be just the number inside, so it's going to be 3i. Well, 3i squared. And then the I squared changes to negative 1, so it's 1 plus 3, and my total is 4. So whether I'm adding or multiplying complex conjugates, we end up with a regular real number. So what complex number can I multiply 3 plus 2i by? Pause here and write it down. In order for it to cancel and become a regular real number with no i's, you need to change the sign in the middle. So we want 3 minus 2i there. And what happens when we multiply these? I can tell that the i's are different. So if I'm multiplying something that's similar but not the same, I am going to get a trinomial. Well, first I get 4 terms, and then when I put the I squared into a negative 1, I get a complex number. So generally speaking, what can I multiply by to get a real number? Well, the middle sign has to change. So I'm going to keep the a and the b, but I have to make it a minus. Anytime I need a complex conjugate, all I do is I change the middle sign. All right, so as complex conjugate definition goes, the imaginary parts have opposite signs. Everything else is the same. The product and the sum will create real numbers. You can go ahead and write down a couple of examples. Try to write down one you haven't seen yet. All right, directions for dividing complex numbers. What happens if I is in the denominator? So if you get a fraction where I is in the denominator, since I is equivalent to root negative 1, and we can't have roots in the denominator, we actually have to do some work to move it out. So we're going to multiply the numerator and denominator by the complex conjugate. That's going to make the denominator a real number because, as we saw above, there's canceling that happens there. You do all your multiplication and you simplify. All right, so if we see, let's set up the top of 24 here. And the complex conjugate, if all there is a 2i, we change the I term to its opposite, and we're multiplying by negative over negative. In number 2, I look at the denominator, I see an I there, so I'm going to multiply by the conjugate here. 2 plus I would turn into 2 minus I. And notice the numerator is continually the same, and that's because I want the fraction to have a value of 1, so I'm not changing or distorting the expression. And the last one was 3 minus I, so I multiply by 3 plus I. If there's an I in the numerator, that's not a big deal. You just leave that alone. And we only focus on the denominator and use its opposite in both locations. So you can pause here and take a little bit to multiply those out. See how you do with those. Okay, so we're going to leave the bottom of 24, or the rest of 24, at that spot. And let's go to, there's more on page 24 here to look at. So if we set these up, put those conjugates on there as well. Notice the sign in the front doesn't change. If it was negative, it stays negative. It's only the middle sign that's changing on each of these. So pause and try them, and I will reveal these so you can check them. All right, make a note of any that you had different and try to follow the path, see if you can figure out where it might have gone wrong if it did, and make a fix. All right, and I'd say we're going to skip over the bottom. We can get this done as well. If I try to factor x squared plus 9, I can't do it because if I do a plus and a minus version, it'll give me a minus 9. So instead, let's think about this. The graph of this would be shifted up 9 units. So there's no x-intercepts. So what I want to do is rewrite this as subtraction. If I do that, I need a double negative to be equivalent to positive 9. So now that it's a minus, now I can factor with the difference of squares. So set up your 2 parentheses and do your square roots. Square root of x squared is x, square root of negative 9 is 3i. And then you do it again with a minus. If you were to multiply this out, the minus 3xi and the plus 3xi would cancel, and 3i times negative 3i would be minus 9i squared, and that's equivalent to plus 9. So we can factor a sum of squares if we use imaginary numbers. X plus 3, x minus 3 is what we would do if it was regular 9 or minus 9, but when it's plus 9, we have to put the i's on there as well. So to generalize, if you're factoring a sum of squares, you do their square roots, but you just make your second parts with i's on them. All right, pause and try these, and then I'll reveal. So just like minus 4, but with 2i and 2i. This one's going to be just like minus 25, but with i's on the 5s. And here it's going to be just like minus 1, but with i's on them. Okay. So that will do it for this section. Your assignment is page 25, so have that ready to go for next time.